Welcome to another edition of Math for No Reason. In this edition, we will be looking at the Euler's totient function, which is denoted as phi n, and it is defined as number of natural numbers which are co-prime to n. Co-prime means that the HCF between that number and n is equal to 1. So there are no common factors between this number k and n. The Euler's totient function phi n is equal to n into 1 minus 1 by p1 into 1 minus 1 by p2 etc. Into 1 minus 1 by pk. Now what are these p1, p2, pk? Now by the fundamental theorem of arithmetic, we know that every natural number n can be written as p1 to the power alpha 1, p2 to the power alpha 2 into pk to the power alpha k, but these p1, p2, pk are prime numbers. And also we know that p1, p2, pk are unique except for permutations. So this p1, p2, pk gets in this formula in this particular form. So how do you prove this result? Now we will first show this result for numbers which have only two prime factors. The motivation being that this would sort of give us an intuition behind the proof, and then we will see the proof in the general case. Now suppose n is equal to p1 to the power alpha 1 and p2 to the power alpha 2. Now let A be the set of all integers, in fact all positive integers which are divisible by p1 and are less than or equal to n, and B be the same. So all these numbers which are in A or B are not co-prime to n. So if we can find out the number of elements in A union B, then n minus the number of elements in A union B would be the number of natural numbers which are co-prime to n. So let's find out the cardinality of A union B. Now we know that the cardinality of A union B is the cardinality of A plus the cardinality of B minus the cardinality of A intersection B. We are denoting cardinality by hash here. Now cardinality of A is n divided by p1. So these are the number of natural numbers which are less than equal to n and are divisible by p1. Similarly, the cardinality of B is n by p2. Now the integers which are in A intersection B are those which are both divisible by p1 and p2. So the cardinality of A intersection B is n by p1, p2. Thus the cardinality of A union B is n by p1 plus n by p2 minus n divided by p1, p2, which is n into 1 by p1 plus 1 by p2 minus 1 by p1, p2. Now phi n, as I mentioned before, is n minus the cardinality of A union B, which is, and this on simplification becomes n into 1 minus 1 by p1 into 1 minus 1 by p2. Thus, if n is of the form p1 to the power alpha 1, p2 to the power alpha 2, we see that phi n is of the right form. This argument we will be able to extend to the case when n has k prime factors. For the general case, we will require the principle of inclusion exclusion, and this is generally represented as PIE. Now, what does the result say? The result says that if we have k sets, then So the number of elements in A1 union A2 union AK is sum over I is equal to 1 to k, the number of elements in AI, minus sum over 1 less than equal to I1 less than I2 less than equal to k of the number of elements in AI1 intersection AI2, plus sum over 1 less than equal to I1 less than I2 less than I3 less than equal to k, the number of elements in AI1 intersection AI2 intersection AI3, etc. And the last term is minus 1 to the power k plus 1 into the number of elements in A1 intersection A2 intersection AK. So this is a very useful principle known as the principle of inclusion and exclusion. We will be using this principle for proving the general formula regarding the Euler's totient formula. So let n be equal to p1 to the power alpha 1, p2 to the power alpha 2, pk to the power alpha k, and we take ai to be the number of positive integers less than equal to n which are divisible by pi. And then we will be applying this principle of inclusion exclusion to get the result. Now the number of elements in AI is equal to n by pi. Number of elements in AI1 intersection AI2 is n by pi1 into pi2. So these are some of the basic raw material using which we will be getting to the final result. And of course, the last one, the number of elements in A1 intersection A2 intersection AK is n by P1 into P2 into. Using the principle of inclusion exclusion, what we get is the first term will be summation of I is equal to 1 to k n by pi. The second term would be sum over 1 less than equal to I1 less than I2 less than equal to k n by pi1 into pi2. The third term is 1 less than equal to I1 less than I2 less than I3 less than equal to k n by pi1 into pi2 into pik, and this continues, and the last term is minus k plus 1 minus 1 to the power k plus 1 n by p1 p2. So therefore phi of n is n minus the cardinality of A1 union A2 union AK, and therefore this is n minus summation of I is equal to 1 to k 1 by pi plus summation of 1 less than equal to I1 less than I2 less than equal to k of 1 by p I1 into pi2 minus summation of 1 less than equal to I1 less than I2 less than I3 less than equal to k of 1 by pi1 into pi2 into pi3, and so on until the last term, which is 1 by p1 p2. Now it is not hard to see that this is n into 1 minus p1 by p1 into 1 minus 1 by p2, etc., 1 minus 1 by pk. And this is the Euler's totient form. This is a good place to stop. Thank you.